Okay, so I guess I need to start because the timer is coming after me. So basically, let me start by saying that what we are going after is the verification of systems that are, typically we'll think of them as unverifiable, and there are different reasons for this. One reason will be that it's too big, and therefore traditional tools that we have are not scalable and will not be able to verify the system completely. And the second reason is the new techniques and algorithms that we use, like machine learning, are to an extent by nature not verifiable because, let's say, at the same time, we do not know what exactly will be the behavior of the system because it's learning, right? So as it learns, it will modify its behavior. So we need to have a different kind of technique. In this case, what we do is actually, instead of verifying the whole system, we add a small piece of software to the system, and this small piece of software will be monitoring the system in general, right? So in this monitoring, it will obviously look for violations to specific properties, and I will use the example of the drone that you have on the screen. And this drone, of course, the example in this particular case is basically a virtual fence. So think of a region that it should not go outside the region. That's the virtual fence. And what we will do is we'll have an enforcer that will check the movements of the drone and find out whether the next movement will take it outside of the virtual fence. If that is the case, then the enforcer will replace that action and put an action that will prevent it from going outside the fence. And that's kind of the idea of the enforcer. Clearly, because the enforcer is small, the idea is that now we can verify the enforcer, right? And that's the idea behind that. Of course, we apply this to distributed systems. And this is kind of the model that we need to formalize this. And the way to formalize this is to define variables that take different values. And we can think of those two types of variables. One are the state variables. So if we go back to the example of the drone, will be the position. Different positions the drone can take, and the actions that are the movements, right? So once we have these two sets of variables, then we can define what is actually the safe region. What are all the positions that are possible to take without violating the virtual fence? And the actions, what are the movements that we allow? And we built a state transition system, and now we can verify the state transition system, right? Once we have the verification, let's say, objective, the next point that we need to go after is how do we define the safe region? So clearly it's just positions inside, but the next region we need to define is what is enforceable. So it means if we are very close to let me call it a virtual wall, right? Maybe and the drone is moving, the inertia actually may make it violate this virtual fence. And it means because I didn't have enough time to brake. So taking into account this enough time to brake, we define what is called an enforceable region or enforceable state, right? And the idea of the enforcer is, first of all, verify if the next action will take it outside of the enforceable region. And if that is the case, we will replace the action with a safe action that will keep us in the enforceable region. So if we put this in the context graphically, if you will, this is the way to think about it. These are the different states, the transitions we take with the movement. And then we can see already there C phi is the enforceable region. And phi is actually the region that we want to keep the drone in, if you will. Right? So, of course, what we will be doing with the enforcer is checking the actions. If we discover that one of the actions will take us outside the enforceable region, we'll replace that. And all of this, of course, is formalized in order to use our verification techniques. So this is an example now with two enforcers. Because the idea behind enforcers is that, well, if we want to add this to a regular development process, we will have multiple components, multiple properties that we want to enforce. And then, obviously, we need to compose the behavior and the verification argument, right? So this means that we need to put multiple enforcers together and verify that the two properties we are going after, for instance, for two enforcers, can be verified. In this particular example, we have the virtual fence, this is that rectangle, and we have also a separation concern. And that separation actually is the one that will prevent us from having collisions, for instance. And we put it as a distance. So then the idea behind the composition is to say, In reality, the enforcer will give me not a single action, but a set of actions that I can take that will be safe. So then we will try to do the intersection between the two enforcers. If there are actions in the intersection of the two enforcers, then I can take one from that intersection. But what if we don't have actions in the intersection? So then we apply what we call a priority-based order of the enforcer. We select one of them, and we drop the other. That's the way to go after the enforcer. Obviously, in this particular case, the idea is that if one drone is against the virtual wall and the other is approaching, we need to violate one of the two, either the separation or the virtual fence, and we decide which one has higher priority. The second way we explored was utility maximization. In this particular case, the state is modeled and the action is modeled as an action within an angle, so that's the angle we are going after, right? So if we are flying against a virtual wall, obviously the angle that is ideal is completely perpendicular and opposite to the wall in the direction we are going after. But if we are going into a corner, then it will be 45 degrees against any of the walls. So that's the way to think about the maximization. Then once we have these enforcers, the question is, are we done? Well, the problem with cyber physical systems is the system evolves by itself because it's physical. We mentioned that the drone is flying by itself, and the next action could be braking, right? If the next action is braking and we do not issue the braking action in time, obviously we can violate the virtual fence, right? So that's the problem with cyber physical systems. And when we have unverified software, one of the problems could be we have an infinite loop. It will never end. So even if we can verify all the actions, all the outputs, right? The problem will be if we don't issue the braking action on time, we can still violate the virtual fence. So we had to add a temporal enforcer, is what we call. So the way to think about this is in traditional real-time scheduling, we will have multiple tasks, and they will have different priorities. So you can see the blue task will have the highest priority because the one that arrives more frequently. The red one will be lower priority, medium priority, and the last one will be the lowest priority. Every time the high priority guy arrives, it will take the processor and preempt the other guys and delay them, right? But our schemes assume that we have a worst case execution time and we can verify the timing. But what if we have a problem with timing? For instance, if it runs forever, if it gets into an infinite loop or takes too long to execute, then the problem is that the expected actuation, these alpha elements that I'm putting there, will take too long to be produced. For instance, if we are at the border of the virtual fence and it takes this long to produce, then we will not see the actuation, we will not see the braking action, and obviously we'll violate this condition, right? Not only that, but it also delays the execution of the other task. So we have two problems, actually. So how do we solve this? What we do is we impose execution budgets. So they will only run during the execution budget in a way that whenever we see an action like the blue guy, the last execution of the blue task, if he's trying to go beyond the budget, we will pause it and resume at the next periodic activation. But we still have the problem of the late actuation, the late alpha, right? We were able to contain the delays on the other tasks, the red and the blue and the green, but still have the problem of this late actuation from the blue task. So what do we do? Then what we will have is that whenever we are about to enforce the budget, what we do is we execute a default action. So think about the drone. The default action in the drone will be to hover, right? If we are moving and we say, hey, we haven't received the action, then what we will do by default is hover. Hover, stop there, while we finish the verification of the value, whether the value and the next movement is correct or not, right? Now we extended this to say, well, then we need to think about a different kind of scheduling. So to say, remember we have this phi, that is the safe region. We have C phi, that is the enforceable state. But we have additional rings concentric, right? If you think about the drone, that's simpler to think. If we're in the middle of the region, it doesn't matter if we don't execute the action in the next deadline because we are very safe. So if we know where we are in the region, right, and we are in the middle, then missing multiple deadlines is not a problem. Some deadlines is not a problem. We can miss them. So we said, can we use that for the schedulability to find out how many deadlines can we miss? So we created a new schedulability scheme, if you will, that talks about the resilience, scheduling resilience, right? And the reason is, of course, we have multiple tasks. A system will have a collection of tasks. If you think of an avionic system, right, we can have the auto trimming, sorry, I cannot see everything, collision avoidance, stall warning. All of these systems together will have different deadlines. And for all of them, we need to have a verification both of the logic and the timing. So that's why we need to do this scheduling, right? So let me just skip this. That's actually what we are doing, how to do this schedulability, taking into account what we can skip, if you will. Okay, so now what we have been doing as well is for the following year is we have a hypervisor. So we talk about, we have enforcers, we have a way to enforce the timing, but how do we know that the scheduler and our enforcers are correct? So we need to have a way to protect them, right? To make sure that they are fully verified. So for this, we are pushing these enforcers in a fully verified hypervisor. That we have a new guy working with us that is using, has been developing what is called a micro hypervisor that is fully verified, and that's where we are gonna now put our enforcers inside this hypervisor. Some results so far. So we have a couple of papers. One is already published. The other is in submission. A couple of things that have happened in addition to that. We have, of course, a number of software artifacts. We have some demos with drones flying around. We have our drone lab where we play with drones. It's a lot of fun and hopefully useful as well. And we have also worked or participated in the Summer of Innovation from AFRL, where during 3 months kind of we team up with other institutions to transition our results into their development environment. This is called UXAS. So we transition our timing enforcer and a logical enforcer there. And of course, we are using part of the results we have in other projects like the ONR YOLO, trying to kind of take advantage of our current results. For the future, I mentioned already that we are pushing our enforcers down to the verified hypervisor. That's what we are trying to go after. In the long term, one of the challenges we have in front of us is that there is nothing safer in a drone, for instance, than a drone that is sitting on my table. Very safe, but that's not enough, right? So we are trying to minimize the times when the enforcer needs to kick in, for instance, to hover. So we're trying to minimize the hovering. So how can we do that? We need to have better ways to express the safety to avoid kind of inefficient actuations whenever we are trying to be safe. So that's the other challenge. And with this, I think I will be able to leave a minute for questions.
I can see applications beyond drones, but
yes,
in terms of manned-unmanned teaming and in the airspace, you've got a community where you've got manned systems flying through. So how do you account for a bull in the china shop going through your swarm?
Well, there are things that are kind of difficult to verify, right? But one of the things we are exploring is, for instance, can we consider failures as part of the unverified behavior, right? So I will try to go a little bit softer than extreme failures, right? But if you think about, for instance, communication failures, typically when we have distributed systems, we try to mask the errors. To say, okay, so if I have an error, I retry, I retransmit, and then I'm able to mask the error to some extent. But sometimes you cannot do that. And wireless communication is a big problem for us, right? Because then sometimes you will have some accumulation of errors that you will have a blackout of communication. So is there a way to change that and say, okay, for that I have a different kind of action, right? It's not a traditional, okay, I'm moving, going back to the drone, but to say, right now I have no idea. I don't have communication, so what should I do? In this case, I will say hover. Not always will be hover the answer, but it's just let you think about a different way to think how to structure these errors and how to reason about the errors, right? So I can assume that for more extreme errors that are permanent, we can do something similar. That would be kind of my answer. Right?
Okay, phase 2 to the question is that airworthiness certification folks don't like things moving on their own.
Yes.
And so when you try to put these into a tactical situation,
Oops.
something I said? UAVs are not going to, they're not going to like I'm going to move on my own without an answer as to how I'm going to move, why I'm doing it, and so forth. And so it's going to create a certification problem to go out for airworthiness.
Right. I will assume that there is a more complex conversation. Absolutely, yes.
Yeah. Does your specification allow for latency and/or error in the state measurement of the drones?
Latency and error. Latency, of course, is part of our idea of the timing verification. But probably there is more to what I'm thinking that you are thinking. But let me go after errors, right? For instance, I will try to do a variation of what I explained already, communication. But if you think about GPS position, you say, okay, I have an error in my GPS position. That could be accommodated in this framework in the sense of, let me put it like this. If we think in a different way to masking, a couple of things comes out of masking. One is, from GPS, you can have a small deviation, and that deviation will take you little by little into a different direction than the one you are trying to achieve. So the accumulation is actually the problem. This also happens with pitot tubes, for instance, in the airspeed, right? We have a pilot in our team, and he's always thinking about this kind of situation. Oh, well, when I fly and I have problems, there is accumulation of errors. As it is right now, we don't have an answer for that, but that's one of the things we are thinking in the future. So how can we prevent this masking idea from really keeping us safe, right? That's the idea behind that.
Okay. And just a quick follow-up.
Yes.
In the case where you have the multiple drones,
Yes.
is it a centralized controller model, or are you assuming a distributed control model executing on each drone?
We can consider this distributed, but our current demo is centralized.
Okay.
Yeah, our current demo is centralized. Yes, correct.